VideoPulse, physiological signal extraction from video. Introduction. Remote photoplethysmography enables non-contact monitoring of vital signs like heart rate and SpO2 using a normal web camera. Let's look at the diagram. Traditional vital sign monitoring methods in neonates rely on contact sensors, which can be intrusive and unsuitable for delicate neonatal skin. Existing rPPG methods are mostly optimized for adults and perform poorly on neonates due to small face size, motion artifacts, and poor ground truths. Objectives. Our work has two primary objectives. First, to create a dataset of neonatal facial videos paired with vital signs, specifically heart rate and SpO2 levels. Currently, very few datasets exist in this domain for neonates, and those that do are primarily based on fair-skinned infants. Second, to develop machine learning models that can predict heart rate and blood oxygen saturation from neonatal videos. For data collection, we used a web camera mounted on a tripod to record videos of newborn babies. A pulse oximeter was used to measure vital signs in real time, transmitting data to a PC which also controlled the video recordings. We named our dataset VideoPulse. Data was collected from 52 neonates at the Soysa Maternity Hospital in Colombo, with ages ranging from 0 to 6 days. The dataset comprises approximately 2.6 hours of video, recorded over 157 sessions with each video lasting approximately 69 seconds. Now, let's take a closer look at the statistics of our dataset. The majority of SpO2 values fall between 92% and 98%, with a mean of 94.4%. The heart rate distribution exhibits a wider range, spanning from 79 to 174 beats per minute, with an average of approximately 114 beats per minute. Let's walk through the basic idea of our system. A video of the neonate or adult is fed into the system, which then processes it to estimate two key vital signs: heart rate and SpO2 level. Then let's talk about the architecture. In our architecture, we use facial videos from adults and neonates as input to estimate heart rate and SpO2 levels. First, we detect and crop the faces, and then the frames are difference normalized to highlight subtle skin color changes related to blood flow. For heart rate estimation, the frames are processed using Rhythm Mamba, a Mamba-based architecture. For SpO2 estimation, we use a modified PhysNet model that outputs SpO2 levels directly from the video frames. To improve accuracy in neonates, we train using clean ground truth PPG signals that are reconstructed and filtered for noise. Finally, we extract the heart rate by analyzing the frequency domain of the predicted rPPG signal. Let's talk about the results. For heart rate prediction, we achieved a mean absolute error of just 2.97 beats per minute on the NBHR dataset. On our own VideoPulse dataset, we obtained an MAE of 5.34 beats per minute. Our method outperforms existing state-of-the-art methods on the NBHR dataset. For SpO2 prediction, we achieved a mean absolute error of 0.8 on adult datasets. On the neonatal side, our model reached 1.69 on the NBHR dataset and 1.68 on our own VideoPulse dataset. This is the first study to predict SpO2 levels in neonates using facial videos. Let's take a look at the demo. This is an application that we built to test the functionality of our models. We can select the dataset that we prefer. Then we can see how it is being processed and inferenced in the remote server. Finally, the results will be displayed in the interface. Here we have the extracted metrics along with the predicted and ground truth, PPG waveforms.